these here. First one, make it tosylate. Also chloride pyridine. No change in stereochemistry. Then we can come in here with cyanide, pretty good nucleophile, considered a strong nucleophile. Sn2 backside attack. Cyano group now on the carbon. Substitution reaction. Sn2 comes with inversion. Yeah? Sodium with the alcohol converts the alcohol to the alkoxide, yeah? We demonstrated that yesterday in lab. Then the good nucleophile. Carbon with the leaving group. Backside attack, Sn2. And we're going to get inversion here. I drew it like this. Oxygen now bonding to that carbon instead of the bromine, right? That is a deuterium. It's a primary carbon. That's just a fancy H. Primary carbon. Sometimes you'll see problems with deuterium because if it was a methyl, it would become a secondary. But it remains a primary. A deuterium allows for stereochemistry. Because one is an H and one is a deuterium. Basically, we have inversion here. You can draw it however you want. This is R. The thing that's leaving is high priority. The new thing is high priority. This is S. It's inversion. You can show it however you want. No change here, though. No change there. Yep. Pretty straightforward. Any questions about these so far? Yeah.
So I see how you drew the arrow like under the bromine reversal. If you drew it like that, would it be considered?
It'd be all right. I mean, all the reason I did it differently is because the bromine is in the plane, so I can come in directly from over here. See up here, the tosylate's going back. I can't show this coming, tosylate's coming forward. I can't show it coming back because I can't write in the background. But here I realize that since the bromine's in the plane, I can draw the line in the plane. It doesn't matter as long as you understand what's going on and show the result, right outcome. You're not asked for a mechanism here. You're asked to show the major product. Now I would think mechanistically. I would use mechanism when you scratch paper. That's like working a formula in math. But I would not grade this. I would grade the answer. The Hoffman product would be, you got a beta hydrogen here. Double bond here would be less substituted. Mono-substituted, that would be the Hoffman product, right? You still have the methyl over here going back. State-cell product, we would want to remove this H, put double bond in here, because that would be a tri-substituted alkene. But this alkene is stereogenic. Are the methyls going to be cis or trans? They will indeed be cis because if you show this compound in a Newman projection and then rotate the HA and have it anti-coplanar to the bromine, this is how it eliminates. The two methyls are on the same side. The phenyl and the H are on the other side. The phenyl and the H, undrome H, are on the other side. How do we do? How we do on that one, guys? Okay. We did Newman's in class, right? I suggested that's how you need to do these. Methyls or cis. React fastest with Sn2, be this compound here. Is that right? Good. Any questions on that one?
So, I was going between the bromine and the chlorine, only because
Bromine and
the chlorine of the two sp3.
this one?
Yes. Only between those two,
What's the better leading group, bromine or chlorine?
bromine. And I understood that. But I did chlorine only because when I looked at the nucleophile / base, I understand that it becomes an anion, but it's not strong necessarily. It's not really strong.
It's strong, it's an anion. It's an alkoxide, which is what you have to generate to do Williams ether synthesis, which is what we generated up here. This is a sodium alkoxide. That's just a potassium alkoxide. Strong. But I also told you it's Sn2, so you didn't have to even consider that.
Yeah, I just.
Bromine's better leading group than chlorine.
Yeah, I knew that.
That means it's going to be an easier, faster reaction. I'm not sure why. So you thought this was Sn1?
No. I still realized it was Sn2, but I was just thinking, I understood that it would become an anion because the potassium would ionize, but when I was thinking.
It's already an ion.
Yeah, but it wouldn't be considered to react with that in that moment as far as the Sn2. Never mind, but I understood it made an anion, but in the form of thinking it as a strong base, I understood even though it becomes an anion as far as its strength, I didn't think it was going to go towards bromine, which is a stronger leading group versus chlorine. So I thought because it was a less nucleophilic anion, it was going to go towards the weaker leading group. So, yeah. I would put it in.
You guys typically use ionization when it's already ions. You're not called that, it does not ionize. You could say it dissociates. It's already ions. Mechanism. The OH is gone. How do you make OH a better leading group? We've got a protonate, we've got a strong acid, H+, protonate the oxygen. Now it can leave, make cation. Ultimately, we need this cation. We can make bond on the end there. Double bond needs to be moved to the center here. We got to recognize a hydride shift. Hydride shift to give this cation. Resonance stabilized, we can show resonance structure, resonance arrow, and then iodide attacks on the end, that gives us the product. Yes?
I have a question about number 3 still.
Number,
Or the one before this one. So why would, I'm comparing the second one and the fifth one. Why would, okay, like wouldn't the second one be more likely to undergo Sn1 since if it formed a carbocation, it would be stabilized by resonance?
second versus fifth?
Yeah.
The second is more likely to undergo Sn1,
But if we're talking about Sn2.
but we're talking about Sn2. Yes. It's also more likely to undergo Sn2. Second versus the fifth one?
Yeah.
Both bromines. What's the rationale here? What's the argument?
One has resonance and one doesn't.
Well, it's not really resonance. It's
Or
it's not delocalization of charge. p orbital next door.
Yeah.
And in the Sn2 transition state with this anion, and these electrons come in here and kick that off, what does the transition state at the carbon look like? It's sp2-like. It like becomes a p orbital-like over here during this transition state. But as that p orbital-like forms, it can interact with the next door p orbital. That's a stabilizing effect. There's no p orbital next door over here, so you don't get that stabilizing effect. Pink sheet. Second page. Why, how is inversion obtained? Number 3, pink sheet, second page. Did we draw the transition state? We talk about p orbital like, sp2 like, lab. Okay. Grace, you good? There's no carbocation board here.
Yeah, sir, I had a question about the mechanism. That's the mechanism I did. I was just kind of confused because I thought that potassium iodide, it would exist as an anion. And so wouldn't that make it a strong nucleophile? In which case, wouldn't it undergo an Sn2 reaction and not an Sn?
Well, I minus is the conjugate base of HI. What do you know about HI?
Oh, HI would be like a nucleophile.
No, HI is not a nucleophile. It's a terrible nucleophile. Strong acid.
Oh, I see.
So the conjugate base of a strong acid is a weak base. It'd be a weak nucleophile. Yes. Yeah. Not all anions are strong. We said that. The opening comment is strong nucleophile anions or sp3 nitrogen. But I also told you things like sulfate, nitrate we mentioned, F minus. And actually, well, I take that back. I minus is actually a pretty good nucleophile. Is it strong? Well, that's borderline, but okay, I understand Yako's, it's more than a halide. Okay. So how did you get that product by doing an Sn2?
I did exactly that mechanism. I was just confused. But no, I did that mechanism.
Oh, so you got it right. I minus is borderline. I mean, I reckon you could say some nucleophiles can it be strong? I minus can actually be strong. It's borderline. That's why it's able to do this, because it can exist with acids. I minus, I reckon, would be considered a fairly good nucleophile that can exist under acidic conditions, because it's conjugate base of a strong acid. I minus can exist. I minus exists in HI. I minus can exist with sulfuric acid, where most other good strong nucleophiles cannot. Like an sp3 amine, it's a good nucleophile. It can't exist with sulfuric acid, because it'll act as a base and it'll react with sulfuric acid, then your nucleophile is gone. Up here, we made a good nucleophile with the O minus. That can't exist with sulfuric acid. If this was around sulfuric acid, it's just going to react with the proton and go back to the original OH compound. So I minus, I reckon, is an example of a decently strong nucleophile. It's not incredibly strong, but it is okay. It can exist with acid because it's the conjugate base of a strong acid. And by definition, I minus can exist with HI. In fact, that's how HI exists, is I minus. So it's sort of a mix. But guess what? You were also not asked to just show a product here and say, and then sitting there, well, it's going to be Sn2. You had this to go by. And thus you know what you need to do. And it sounds like you got it right because you knew what you had to do to get to that. Yes. Because you got to have a rearrangement and you got to have resonance and all this, and you only get all that with carbocation. And so we got to form a carbocation, and so the leaving group has to leave. Before it leaves, what do you have to do? You have to make it a better leaving group, right? Because OH is not a good leaving group. And when we say leaving group, that applies to any of the reactions we're doing, Sn1, Sn2, E1, E2. Leaving group ability is the same with all of them. What's the best leaving group for Sn1? Iodide. What's the best leaving group for E2? Iodide. What's the best leaving group for Sn2? Iodide, okay? Iodide is the best leaving group. Phosphates very close. Bromide, and okay. Question?
Wouldn't iodide want to attack the secondary instead of doing a shift? When you do the shift, you have a primary carbocation.
No, where? That's secondary.
Then you go there. Then down at the
And
bottom,
this is,
that's secondary. Then when you go down to the bottom, it's the primary.
yeah, but neither one of these are real. This is one thing. The true structure is what?
It's a monomer.
It's a blend. It's a blend of secondary and primary. Okay? Secondary and primary. Which is better? This, which is only secondary, or this cation, that's one cation, or that cation which has a blend of secondary and primary? Which is better?
I would think just secondary.
Okay, I could see that because you think this looks bad. Well, this is actually good because the charge is delocalized. It's like, that is bad, but at least it's delocalized. It's delocalized. Now the charge is delocalized over two different carbons. And while this may not contribute much because it's primary, at least it's something. Where this is an isolated, which is better? Resonance stabilization or non? Right, resonance. We went over here and we were able to do resonance now. The charge is now delocalized. You can't say this is secondary or is it it's a blend. It's delocalized. Yes, it would be better if it was secondary, or secondary, tertiary, but it's delocalized still. And you have to get the product, because if you did do a hydride shift, how are you going to get that over there? How did you get there if you didn't?
I got there. I used that way, but I was just wondering when I was doing it, I saw a primary and I was just confused.
Could the I minus attack here?
Yeah.
It's possible. Maybe there's other products formed here. Maybe this is not even the major product. Maybe this is a very minor product. But it's a mechanism question. It's asking, how do you get to that product there?
So I have a question.
It's not a predicted product. Yeah.
So if you hadn't given us the product and we didn't resonance stabilize it, put that primary?
If I didn't give you the product there, they could have been multiple. Again, you could have done an Sn2. I mean, you could have did, if you hadn't been given a product here, you could have just came in here and kicked that off and said, hey, I'm going to propose that the product is, well, there's no stereochemistry shown here, so I don't know what to show, so I'm just trying to show generically. I mean, you could have said, hey, I propose this by an Sn2. Protonate and then do an Sn2 and kick off the leaving group. Because iodide, as we mentioned, is a decent nucleophile. You can predict this. You can predict a hydride shift and have an iodide add here. See, at this point, we can ask. This is one thing. Where would the iodide rather add? Would you rather add here or here? No, you'd rather add here. Why? Because the resulting product is disubstituted. And added here, the product would be monosubstituted. This is just like the second half of a dyeing reaction. The halogen now has a choice. Does it add this or that? How do you decide? If there's a choice, it's going to be thermodynamically controlled. And so I hope you would predict this. And by the way, did we use HI in this reaction? No. But we did have H plus and I minus. Which is what this applies. Doesn't this apply H plus and I minus? Okay. See, HI is actually not that common. It's just not that stable, and you don't see it around a lot. But these two are super common. And so you get your H plus from that, and you get your I minus from that. Yep. Mass spec, second one, is that right?
Yes.
If you look at the masses, the last two are 88, but this says, this looks like an 86. So we can get rid of the last two, yeah. And of these three, it looks like we have M minus 43, which is a propyl group. The second one, we complete with propyl to give an acylium ion. And I showed the acylium ion there. How'd we do? Okay. Test tomorrow, similar format as other tests. We have nomenclature of dyings, right? We have chemistry of dyings, 1, 2, 1, 4 additions, deals all the reactions. We have resonance, applications of resonance, including like some acid-base chemistry, which we actually first looked at during test 1. Look at your acid-base handouts on test 1. There's a section on resonance, yeah. After dyeing chemistry, we had mass spec, yeah. Mass spec problems like the ones in the workbook and maybe like here. Then we have substitution and elimination reaction. 2 handouts there. Obviously, there will be mass spec. There'll be short answer, multiple choice, predict the product, and mechanism questions. Very similar format as before into the quizzes. Question?
Yes. For the SN1, SN2 packet, I know that the one on like the first sheet had strong acids that we were using, and the leading groups.
First page?
This page, yeah, this page. They were on secondary carbons. Had you not given us the product, how would you want us to do both SN1 and SN2? Or would you specify?
Which one?
Just in general, because if you didn't give us the product, we just had the.
Well, you talking the first one? Let's look at the specific one.
If we looked at the first one and you didn't give us that product to get that through the.
Okay, because the leaving group, or can this be a leaving group? We've got to have some acid.
Yeah.
Do we have acid? Yes. Okay, H plus. It's on secondary carbon. Okay. So is it SN1 or SN2? Well, the answer is it could be either. And that was in the summing it up section. Okay, it can be either. So
I just wonder if you wanted to show the SN1 and SN2 product, or we can specify, show.
Well, again, this, as shown, it's a mechanism question.
Yeah.
So you didn't have to make that decision. That's the first point, right? Now, if it wasn't given, how would you do it? It can be a little tough. Unless maybe you were given, and remember the previous quiz, I gave a little rate information. It said if sodium chloride was added, the rate increases. That tells you that chloride must have been the rate determining step. That means it must have been a SN2, because only the nucleophiles involved in the rate determining step of the SN2. So I gave you a little extra information there. Why? Because of the reason you're asking, because you had to, it can be difficult. Yeah. I kind of feel like this would be an SN2 because here on next door it's going to stabilize that Sn2 transition state. But it could be SN1. But again, perhaps some more information could be given. In the mechanism, this tells you the mechanism right there, which is what? Yeah, that's SN1, because SN1 gives racemate. And so that was the key information here, you know. Because down here, it's also an alcohol with HBr, but down here we got inversion. So this is SN2. So stereochemistry, but again, you're talking about if nothing is given.
Yes. So we just give.
I kind of feel like this is important, but it can be tough. Perhaps other information is given. I'll post this quiz key upstairs, but I'm not going to do a video key because we did it here in class. Let's look at blue sheet elimination. Let's finish that up. How about this mechanism here? What are we doing it? Mechanism here, this alcohol here, it's actually a diene. It's a non-conjugated diene, yeah? Non-conjugated diene. Treat this thing with acid, aqueous acid here, we get, anybody remember the name of this compound? You ever use that compound? Oh. Orthoxylenes, used as a solvent for the solvent reaction. Yeah. Mechanism, somebody got it? Anybody got it? Anybody else? Obviously, the oxygen is gone. Everybody agree? Oxygen must have been leaving group.
No, water.
It will protein
Okay, well, yeah, but oxygen is part of the water, yeah. Okay, what do we do? Usually under acidic conditions in a mechanism, first thing you're going to do is you're going to protonate something. Okay? That's a little clue. Protonate. Otherwise, you wouldn't be using acid. Usually acid is there to kind of get something kick-started. We got H plus and water, we can just draw this like this, yeah? These electrons here. And we have the oxygen is now protonated. It's a positive charge. We have double bonds here, and we got two methyls there. I'll just do those line bonds. Yeah? Looks good? What can happen next? We got water. We got H plus in water. I mean, how about leaving group leaving? Can it just leave? What type of cation are we going to make if that just leaves? Is that cation any good? It's secondary, but it's more than secondary because it also has resonance. It's actually doubly allylic. We can do resonance here and here. It's very resonance stabilized. The charge is very delocalized. We see pi bonds are sort of moved. What if we windshield wiper this down here? What does that give? Well, that's a resonance structure. Resonance arrow, yeah? That there. I got to connect some bonds over here. That there. Positive here. Two methyls there. Yeah? Which is resonance. How can another methyl end up over here? Alkyl shift. But this is not resonance, because we just broke a sigma bond. Now we have methyl here, methyl here. Where's the cation now? On this carbon, because it lost the bond, it lost the methyl group. How do we get final product? Well, there is an H here. You got to recognize that. Okay? See, how many H's on that carbon? Could ask that on day one. 1 H. How many H's on the carbon now? 0. Well, at this point, this is just the old fast beta elimination, the second step of an E1, where something takes the H and the pi electron, these electrons fall in as a pi bond. What can take the H? How about water? Take these electrons fall in. What does that give? Gives product. What did we reform? H3O plus reform. That's actually catalyst. But what did we make in this reaction though? What did we make new? Right here we made something. This plus water. We actually made a water. If you balance this out, it's plus water. Because this is an elimination. It's basically this. We eliminated water. If you take the formula here, remove H2O, you now have this formula. So that can be called a dehydration reaction. And we had previously saw dehydration reactions over here. Alcohols commonly dehydrated with sulfuric acid by an E1 mechanism. The only thing is, in this mechanism, there was a little bit more than just cation and then beta elimination. We had cation, and then we also had resonance, and we had an alkyl shift. Then we had the fast beta elimination. Because cations, you've got to always be aware of what? Rearrangements and resonance. And this is just, okay, from now on, anytime you see a cation, no matter how it's formed or what mechanism, they're always prone to having rearrangements and being subjected to resonance. Cations are commonly stabilized through resonance. But the resonance can get you another structure, and then maybe your product comes from that other structure. But remember, once you start doing resonance, neither one's really correct. It's really a blend. How many intermediates in this mechanism? How many total intermediates in my mechanism? Three, right? At the protonated oxygen, We have the carbocation. This carbocation, this is one thing. I didn't show the hybrid of that one thing, but it's, okay. This intermediate, and this, I rearrange. That's different from that. There's different energies. There's different sigma bonds. But you got, that's one thing there. Like in my mechanism, I made something that was pink, but I just didn't show it pink. I showed it red and white. I said, hey guys, it's really pink. Right? That's the idea of resonance. Okay. Polar solvents promote ionization. Okay, deuterium isotope effect. A neat way to determine if an elimination is E1 or E2. E1 or E2. Of course, back over here, you already have thought about this. In which elimination mechanism is the beta hydrogen abstracted in the rate limiting step? I'll ask that again. Very important question. That's why I included it in my handout. I don't like to include things that aren't important. And which elimination mechanism is the beta hydrogen? Anybody? E2, right? Okay. You need to know such questions, such things about your mechanisms. Look at this reaction here. If we take this alkyl bromide, and Janelle, we're fixing to figure out how to determine if it's E1 or E2 when it becomes questionable. Because, is this reaction here shown? Pyridine. Is this it's an elimination here. We're eliminating HBr, make it alkene. Is this E1 or E2? E1 or E2? Yes, it can be either one. Question is it E1 or E2? All right. Would you like a neat way to determine the answer? Okay. Yes. Why can it be either? Why is it not straightforward? Why is this reaction not easily determined? Why is the mechanism not easily determined by looking at this reaction?
So nitrogen is sp2.
It's sp2, and thus?
And thus it's not as strong enough nucleophile.
I call it base here.
Well,
The
base,
elimination
yeah.
reaction is just that thing acting as base.
Would be a base.
It takes an H.
Exactly. Exactly. And then the heat notation, so you already know it's elimination, but then there's some secondary area on the alkyl bromide.
Secondary halide. Can we make cation here?
Yes.
You can. It's not great, but you can. So it could do E1 via carbocation. Because the carbocation, once you form it, you could do a fast beta elimination, put in the double bond. Could it? Yeah, it could make it, okay, yeah, you could. Is this strong or weak? Well, we said sp3, sometimes when I say that, sometimes sp2, Question is this strong enough to do E2? E2 requires a strong base. Is that strong enough? It's borderline. It's borderline, okay? This can do either. That's borderline, so what is it? Could we determine it some other way? Yes. What you can do is, you can repeat this reaction and replace the H that's being removed, the beta hydrogen, replace it with a D, deuterium. Then do the reaction. Now that may be quite difficult to get a D there, but sometimes it's easier. I'm not going to worry about that. It can be done. Replacing the H with the deuterium. Then do the reaction and look at the rate. Now importantly, the CD bond is stronger than the CH bond. Partly because there's a mass difference, and mass does affect bond strength, and you can look that up. And what's the difference in mass between an H and a D in terms of percent? The D is what percent more mass? What's the mass of H? What's the mass of D? 2. That's an increase of what percent? 100% more. That's a huge difference in mass for isotope. What if you went from carbon 12 to carbon 13? What's the difference in that percentage? Not 100%, because 12 would have to go to 24 to be 100%. So it's much less of an increase. But when you're going from H to D, that's a huge increase, relatively. And mass does affect bond. So in the end, a CD bond is stronger. Okay? If the beta hydrogen bond is broken in the rate determining step, if we make that bond stronger, will it make the reaction more difficult? Yes. A stronger bond is going to be more difficult to break. That only matters if the bond's broken in the rate determining step. So we should only see a difference if the bond is broken in the rate determining step when we change C to D. If we change C to D and the rate becomes slower, that means the reaction must be E2. It means the bond is broken in the rate determining step. But if we change it to CD and the rate doesn't change at all, that means that this bond must not be broken in the rate determining step. It must be broken in the fast step. And if it's broken in the fast step, that means the mechanism must be E1. Okay? Rate difference. This can be shown like this. This is rate with H versus rate with D, or ratio. If the rate with D becomes slower, that means the rate with H is higher. Maybe it's just some arbitrary number, like the rate here is 8, this is 2. Well, 8 over 2 is 4, that's greater than 1. The rate of, okay, just some simple whole number. But if there's no change in rate, if this is 8, no change in rate, that would be 8. 8 over 8 is 1. Okay? So, in this case, with D, does it get slower? Or does it stay the same? This is called a deuterium isotope effect. Or more broadly, an isotope effect, in this case, deuterium. There could be other isotopes you may encounter. This one we're looking at deuterium, which we defined and discussed on one of our first handouts of the course. All right. So this is some extra information that you could be given or asked to consider whenever you're looking to predict a mechanism. I don't know what the answer is. I don't know if it's E1 or E2. I don't have the
Rate information.
I don't have the rate information. But I'm suspecting it could be E2, but again, I don't know, it could, maybe not be. It's tough. Special topic to turn over. Actually, you're seeing deuterium more and more in drugs. Because of that bond strength, this is an HIV drug, and then the body is metabolized at this carbon here. An OH group is introduced. Now there's a CH there. When we metabolize it, the CH bond is broken, and that becomes a CO bond. I think in this case, metabolism, basically, the drug is no longer active once it's metabolized, once this happens. It's a small change, but sometimes it can be major. The drug's no longer active. To make the drug last longer, we'd like to inhibit this metabolism. And one way drug companies are finding they can inhibit metabolism is changing this to the D and making this bond stronger. Now it's more difficult to metabolize, assuming that the CD bond is broken in some rate-determining step of the metabolism. Now it used to be they would put something here like an F, which is a strong bond, or chlorine or something. But now you've got a bigger atom, and it's much different from an H. But replacing it with a D is a much more subtle change in terms of size. But you do have a stronger bond now. And the stronger bond can keep the metabolism from happening if you don't want it to happen. So again, that's an isotope effect. Okay. Let's finish this up. Substitution elimination product for fine reactions. Anybody have a substitution product here? Pretty straightforward, yeah? Substitution product by Sn2. H is not a leading group, and a deuterium is not a leading group. Because the deuterium is just a fancy H. Somebody have an elimination product? Will it be E1 or E2? I'll draw it over here. Sn2 product, E2 product, everybody agree? Questions about that one? Everybody good with that?
Okay, never mind. I was thinking like, I guess the D, since this is special H, would be the one that would be the H that would like leave, but it'd be the other H going Is that why it forms that?
Well, we're doing E2, so the H and the leaving group need to be anticoplanar.
And the D doesn't count as the actual H.
And the what?
The D isn't gonna act as a normal H would and be the one that would leave.
It could, but will it here? Because we also have H there, right? There's two here, one going back, one going forward. Both the H and the D can be anticoplanar to the bromine. So you have a choice.
So would it,
So which one is going to be eliminated?
I guess the H would be eliminated
Why?
faster because
Why?
it's lighter.
Well, not because it's lighter, I mean, that's partly. Why?
The bond is weaker between the C and
That's
H.
weaker
than
bond.
C and D.
It's the same consideration. I mean, when you have a choice, is it going to be easier? The bond is broken in the rate determining step, right? The H, the CH bond or the CD? Well, which one's easier to break? CH.
What's the purpose of the other reaction?
Now see, what if there were two methyls here? Now there's only one way to evade elimination, E2. And that is for the D to be eliminated. And you could, it would just be a little more difficult, but it can be. But see, there we don't have a choice. If there's not one over there. But as drawn, you have a choice. Yes, I would eliminate over here with the H that's anticoplanar with the bromine, or trans there, okay? E2 product, yeah. Down here. Substitution. What's going on down here? Ethanol, silver nitrate, heat. Something was said earlier that I didn't comment on, but I maybe should. You see heat, and you have a choice between, is heat a substitution or elimination? No,
Sn2.
no. A lot of Sn2, a lot of substitutions require heat. So you can't think that just because you're heating, it's going to be elimination. Many substitutions require heat. The point about heat is, the more and more and more you heat, the more and more you favor elimination. I think we've talked about this before with somewhere else. With Diels-Alder, I think. When you heat Diels-Alder too high, it'll start reversing. But that doesn't mean that you don't have to sometimes heat to get a Diels-Alder to occur. It's just more heat. And maybe substitution occurs at 100 degrees, but if you heat it at 200, then elimination starts being favored. So you can't just say, oh, it's 100 elimination. No. It's more of the, when you start going, see, you're going up and up. All right. I mean, here, I see heat. Does that mean, oh, it's elimination? No, it could be either. So what's the substitution product here? Substitution product here. I'll just abbreviate that as an ethyl. And that is going to be racemic, right? Everybody good?
Does it attaches ethyl another, like ETOH, or does it just attaches the ET?
Originally, there's an H there, but we lose the H to go
What
neutral.
takes the H then?
Do what?
What takes the H?
Water.
Well,
Yeah, I can do that.
In this reaction, it'd be nitrate would take the H. Mechanistically, what's the first step? What's going on here? What's the purpose of the silver nitrate? Yeah, it can coordinate with the halogen. It's akin to protonating the halogen. Halogens really like silver. That chlorine's going to start coordinating with the silver, and then it's like, oh, I need my electrons back. Well, sorry, carbon, I'm gone. And that can give what? Carbocation plus what? Silver chloride. And that'll form as a precipitate. What happens next? Hydride shift. Cation here. New H here, one remaining H there. Yeah. Why would it do a hydride shift? Now it's resonance stabilized. Now it's benzylic. I don't have the benzene ring drawn in, but it's benzylic now. Resonance stabilized, benzylic cation, very good. What attacks the cation? The weak nucleophile. And we have the oxygen with the ethyl group and an H. That's positive. Okay, what can take the H? There's no water here. You might have some water to dissolve some of this, but assuming there's no water. See, in previous mechanisms, maybe the Cl minus took the H and we made HCl. But here, the Cl is gone. It's precipitated with the silver. But we do have the nitrate around. Okay? And nitrate is, I'm going to draw it all out. It's sort of big. Minus, plus. If you draw a Lewis structure of nitrate, it's minus. Silver plus, nitrate minus. That's net minus. You can have one of these take the H, leave the electrons behind. That gives 2 lone pairs here in the alpha group. Plus what? HNO3. You can draw that out. You put an H here, OH. That's nitric acid. So as presented, it looks like nitric acid would be formed here as a byproduct. But the silver is going to team up with the chloride to make insoluble silver chloride. And we did a substitution, but it involved a rearrangement. Overall, it's an Sn1 because we had a carbocation. Because we don't have a strong nucleophile. To come in here and kick that chlorine off backside, you need a strong nucleophile. There's no strong nucleophile here. Nitrate is not a strong nucleophile. Ethanol is not a strong nucleophile. Okay, elimination product. Well, will it be E2 or E1? E1. And E1 is the same as Sn1 up to the point where you eliminate it. It's basically the same thing, except from here, you can eliminate. And instead, something takes the H. Well, you can also have the nitrate take the H. It could act as a base. But it also acted as a base in the previous reaction, which took an H. And have these electrons move in and put pi bond in here. Because there's 2 fates of a carbocation. A nucleophile can attack the carbocation, or you can remove a beta hydrogen and put a pi bond in. If we do that, we're making an alkene. What's the alkene going to look like? The double bond is between here. Are the two groups, the phenyl and the other end, are they going to be cis or trans? They're going to be trans. How do we know that? How do we know they're going to be trans? Do we have to do a Newman projection? No, that's for E2. How do we know it's going to be trans? What product do you get? This is essentially an E1. What product are we going to get? Arfan?
I don't know if I said it right.
E1 always gives,
It's on the second or third page.
Zeta? Yes. I was about to say I gave you exclamation points, but I did not. But I did underline it. I said it's always a major product in E1. What is always a major product? It's in bold. The most substituted alkene. Well, we're really not looking at, we're looking at stereochemistry here. What, was there another possible alkene? Actually, no, there's no beta hydrogen over here. That's the only place you can put the double bond in. So that really doesn't apply. We really have to look at the most E1 always gives the most stable product. Up here, which one was the most stable of these two? Yeah, with E, most stable. Or you could draw it, or you can draw it cis. Which one's the most stable? Trans. Okay? That's stereochemistry, not regiochemistry. Okay. So up here we had a strong nucleophile base. Those were bimolecular reactions. Down here we had weak nucleophile base. This was unimolecular reactions. Carbocation chemistry down here. Up there everything was concerted. Backside attack in the substitution, or in the elimination it was the concerted beta elimination. E2. Last thing here, double E2 elimination. Can it be done? Yes, it can be done. You can eliminate twice. You take this vicinal dihalide here, vicinal dichloride, treat it with two equivalents of potassium butoxide. You can do a double elimination. First off, you can eliminate HCl. Well, this one you have to decide, and it's a tough decision. You got H here, you can eliminate HCl here and put double bond in here. Right, if we do that. Strong base, put the double bond in here. That's got lots of considerations. It's going to be, we got terbutyl there, and chlorine here. It would actually be trans. There's two H's here. Yeah? Remove HCl. There are two H's here. Both of them, you can rotate this, both of them can be anticoplanar to the chlorine. When you have a choice, we're going to make the more stable alkene. But this can actually eliminate again. We got an H here. And we can, if we eliminate HCl here again, we'll get a triple bond. Do elimination again. Remove HCl again, put in another pi bond here. We are kind of breaking a rule here, and that's where we'll kind of end up here at. What's quite unique or looks odd about this second elimination? Micah.
We have a drawing right now.
Okay, well that's good. That's not what I was thinking about, but yeah, the HCl are Sn2 Can an E2 occur Sn2? Yeah, exactly. It can. Anticoplanar is easier and more preferred. But maybe this is the product. And it can eliminate here. Yes, it is Sn2. It can eliminate. The other thing was related to the leaving group. What's odd about this leaving group here in this? The leaving group here is not on a tetrahedral carbon. It's on a trigonal planar carbon. And that's sort of breaking a rule. Now, there's many exceptions. I give you these opening statements, because this is like 99% of the time. This is a 1% time where we'll see a halide there. But because of that, that second elimination tends to be a little difficult. And you guys are doing a double E2 in lab this week. It requires kind of a longer heating time. Actually, 30 minutes is really almost not enough. Really, put it on go to lunch or overnight. Let it heat for 8 hours or something overnight. Okay, 30 minutes is pushing it. That's why some of you yesterday had a little starting material left. Well, you can also get an intermediate, and I'm not sure why where that would be on TLC. But this can be a little difficult because the leaving group is actually not on a tetrahedral carbon, but it can be done as well. Just like Sn2 can be done. So you got two things here. If this is going to eliminate, it has to eliminate Sn2 and it has to eliminate a leaving group from a non-tetrahedral carbon. So this tends to be a little bit difficult, but it can be done. You can make alkynes this way, and you're making one in lab this week. Okay? It is a double E2 elimination. You're basically removing HCl from this twice. Each time it's a concerted mechanism. Boom, 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 once, and then you can do it again. Boom, boom, boom. You put in the other pi bond, concerted mechanism. Okay, can be done. That's vicinal. Because it's vicinal, I remove this chlorine first. It is possible that we eliminate the other chlorine first. I'm not going to get into that. Down here it doesn't matter. There's only one way to eliminate first, that is HBr. Because there's no, the halides are on the same carbon. You eliminate HBr here. And we're going to get double bond here. Again, it will be trans because you got two H's here. You have a choice. When you have a choice, you're going to get the better product. And, well, hold on. It'll be more than trans. There'll be a bromine here. It's going to be E or Z, which is bigger. I reckon phenyl's bigger. I reckon the other group would be trans to the phenyl. Ethyl, double bond here, ethyl. And so we remove one HBr. We get that. Now we can come back and remove the other HBr, and from here, this is transcoplanar. Yeah? And so remove it here, and you end up with triple bond, phenyl on one end and alkyl on the other. But now it's linear, and you have no stereochemistry. Right? Double E2 elimination. Eliminate 2 HBRs using strong base. 2 equivalents of a strong base. It is possible, and that's the lab you're doing this week. Using the vicinal dibromide you made earlier. Okay, at this point, I'll see if you have any questions at all about. Anything at all? Any questions at all? Alex?
Oh, no.
I brought this with me if you're interested. You can find flow diagrams or flow charts or whatnot for predicting reactions. Deciding which reaction is going to take place. You can find these. First question, is there an sp3 carbon with a leaving group? Because if there ain't an sp3 carbon with a leaving group, you ain't doing any of these reactions. So that's the first thing. Leaving group chemistry. Although we know that's wrong because we just did a reaction that did not have a leaving group on sp3 carbon. Made the intermediate, right? Well, based on what we just did, we now know that, what kind of chemistry can you do here with this alkene? We can eliminate HBr and make a triple bond, right? Using some type of base, maybe potassium terbutoxide. Right? Isn't that what we just looked at? So that right there makes the first question actually not right, because this doesn't have, that's not a tetrahedral carbon. But again, big exception here. So go back to generalities, okay? Is there an sp3 carbon with a leaving group? Typically, what are good leaving groups? Halides or what? Sulfonate ester, that's a tosylate. Okay? So let's assume you got a leaving group on a tetrahedral carbon. Well, guess what? All 4 mechanisms are possible. Well, is there a beta hydrogen? Well, if there's no beta hydrogen, guess what? You ain't doing an elimination. Right? See, that's something where you already knew that, but you didn't know you knew that. Right? Well, if you got a beta hydrogen, well, guess what? Well, all 4 mechanisms are still possible. Is the beta hydrogen coplanar with the leaving group? I'd rather say this, not is. Why come nothing will write to that? Can it be? Okay? Not is it, but can it be? Because you make it rotate it, right? Right? We rotated it? Yeah. Well, guess what? If it never can be, then guess what? You can't do an E2. But you knew that already, right? What if you can rotate it? Well, guess what? All four mechanisms are still possible. Is there a strong base present? If there's a strong base present, you can do E2 or Sn2. Of course, if you do Sn2, we call it strong nucleophile. Now, this flow chart is distinguishing between very strong and strong. I've not done that. I wouldn't do that. Because if your base is like super, super, super strong base, it'll prefer E2. It'll just prefer to act as a base. I kind of told you that. I told you if it's a good nucleophile, I'd rather do substitution, and bases rather do elimination. Well, if it's a super, super strong base, it's really going to favor elimination. That's all they're doing. We kind of knew that already. But if you don't have a strong base, you can't do E2, because doesn't E2 require a strong base? But you can still do the other three. I'll send you this by email if you want it. But you know all this stuff already. All right? And I don't like to give you this because you guys tend to want to memorize it. I'm showing you this because you know most of this already. Let's look at structure of the substrate. If the leading group, apparently they use LGP, I just use LG. If the leading group is on tertiary carbon, well, guess what? Sn1 or E1 is possible. Looks like we ruled out something. We ruled out Sn2 because you never do Sn2 on tertiary carbon, right? Okay. What if leading group is on primary carbon? Sn2. Because you never do E1 or Sn1. Because those involve making a carbocation. You don't make a carbocation on primary, so it would be Sn2. What if leading group is on secondary? Well, they're all possible. Maybe you look at solvent. Because a protic solvent, we didn't look at this too much. What did we say about solvents? Polar solvents promote ionization. That's where we really didn't look at solvents as close as that, maybe. Over here, we did look at this. If it's on tertiary, it's going to be carbocation, right? Solvent. We looked at this. And I don't agree with that. We looked at polar solvent promotes ionization. That's what I would know. What is this over here? This came from E1 or E2 possible. Oh, no E2, E1 or E2 possible. Same thing, look at substrate. It's just a repeat of over here. If leading group's on tertiary carbon, you're going to be doing Sn1. Anyway, down here, I reckon we finally made it down to Sn1 or E1. How do you decide? Maybe heat? Yes. Again, I reckon so, because that's between Sn1 and E1. If Sn2 is possible, Sn2 may require heat. This makes sense. Didn't we say that heat favors elimination? Yeah. You just have to be careful because you can't always say it's heat. Or you can't always say it's elimination. Basically this is here, but you really don't want this. It can be confusing. You agree?
Yes.
Yeah.
Sorry, I'm not sure.
Yeah. But that's basically what, okay, there's decisions to be made here. And this is one of the reasons I do my test 2 and test 3 differently than most faculty here or anybody. Most organic ones taught by other faculty here, you do this chemistry first, then you do alkene chemistry. I do alkenes first. But alkenes to me are more straightforward because you have name reactions and you're more like, okay, I see BH3, I know what I'm doing. I'm doing a hydroboration, I'm doing an antimicrobial hydration, I know my product. You don't have to quite think as much, a little bit more kind of memorization. Here, you have to think, you have to assess what you got. Okay? You have to assess your carbon with the leaving group. You have to assess your nucleophile. Okay? Maybe you have to assess conditions, rate information. I think it requires a little more thinking. And so that's why I've always sort of stuck with reversing alkenes and this type of chemistry. Okay? It's more and more thinking. If you're just trying to memorize, you're going to probably run into problems because you're going to forget, oh, I forgot that, I forgot this. It's more of a holistic approach of assessing the reaction. All right. I do have lab reports from the Tuesday, Thursday group. And we'll see if there's any other questions. Let's pass these back. Anna? Morgan? Olivia? Taylor? Emily? Jasmine? Is there anything that we need to go back and look at? On the very front of the elimination, there was this reaction where they did elimination 63 to 64. Iodine leaving group, DBU as a base. And then putting double bonding here. Taking the H, electrons in, iodine off. There's also an H on this carbon. Do we need to be concerned about this H being eliminated and putting a double bond in here? Question?
For Williams and Anderson disease, for example, in your workbook, I had something different than your answers, but I wanted to know if it still worked. You have to listen to this on electric, so if you look it out, I chose this on electric, but I got
If you were going to use the
Yeah, the mechanism, I think about.
On this one, everything comes back to this one. There's six to start with.
Yeah, but I see it like, it's quite right in there. I already finished it.
So they can slowly run down. Wow. You are.
So guys, what do leaving groups do? They go bye, bye, bye. All right? That's what they do.
Let's go.
I'm doing cancel tonight. Elimination's going alright, but